My name is Jose Martin Ramos Diaz. I am a postdoctoral researcher at the University of Helsinki in Finland, and I went last year to France in order to conduct research as part of the short-term scientific mission sponsored by Coast Action FP1405. The title of my research is Rheological Characterization of NFC silent-based hydrogels cross-linked by tannic acid and examination of hydrogel structures with scanning electron microscopy. The objective of this study are the interaction in the ternary system, conducting viscosity and rheological measurements on hydrogels and its components. In this particular case, I meant nanofibrillated cellulose, silane, and tannic acid. The second objective was to examine the internal structure of hydrogels with scanning electron microscopy. I will start by describing the materials I used in order to obtain the hydrogels/hydrogels. The first one is the nanofibrillated cellulose. This is a pseudoplastic material made of nano-sized cellulose fibrils, originally obtained by the high-pressure homogenization of wood pulp. This material was obtained from UPM as a dispersion containing 2.65% concentration of NFC. The second material I used to obtain hydrogels/hydrogels was birch silane extract. Birch silane is a plant cell wall polysaccharide that can be obtained from side streams of forestry industry. In this particular case, this extract was obtained from beer sawdust following a pressurized hot water extraction process that is detailed here in the slide. On the right side, you can see some parameters of the process, such as temperature, wood-water ratio, flow rate, and extraction time. If you want further details on how this extract was obtained, you can refer to Kilpeläinen et al. 2014. The third material I used as a component for hydrogels and hydrogels was tannic acid. This is a polyphenol that is widely available in plants and commercially obtained from gallnuts. The company we purchased it from is called ACS Reagent Sigma Aldrich. The process flow I followed in order to obtain hydrogels and hydrogels is shown in this slide. I started by dissolving birch silane in deionized water by heating up the system to 80 degrees Celsius and stirring it for 30 minutes. Then I mix it with NFC and tannic acid, and this mixture was homogenized with ultra durax at 1100 revolutions per minute for 15 minutes. The resulting suspension is what we call hydrogel. If we wanted to obtain hydrogels, then these hydrogels were cast into square petri dishes. These were freezed at minus 70 degrees Celsius for 48 hours, then freeze-dried for 48 hours more, and the final product was stabilized at 50% relative humidity. Regarding the results, the relative viscosity of silane solutions increase in proportion to the concentration of silane. As you can see on the left side of the slide. However, only minor differences were observed at temperatures ranging from 20 to 50 degrees Celsius. As expected, the intrinsic viscosity of silane solutions between 20 and 50 degrees Celsius showed also minor variations. In this case, the variation is between 0.0932 and 0.0954. In this slide, we can see the results of the preliminary test I conducted by mixing silane and tannic acid. This combination led to the formation of a suspension, as we can see on the right side of the picture, and at larger concentration, the formation of a heavy precipitate. In the table, we can see how the a solution containing 0.5% silane reacts with tannic acid, leading to the formation of no precipitate. But if the solution of silane is 1%, then the concentration of tannic acid could lead to heavy precipitate, especially at 4000 ppm. After knowing that tannic acid and silane would lead to the formation of suspensions and eventually the formation of a precipitate, then we could set the parameters to prevent the formation of heavy precipitate, and therefore used the capillary viscosimeter in order to measure the relative viscosity. On the left side, we can see that the relative viscosity of various tannic acid concentrations, in this case from 1000 to 3000 ppm, in a solution containing 0.5% silane, showed only minor variation around 1. In a similar case, the relative viscosity of various silane concentrations in a solution containing 3000 ppm of tannic acid also showed negligible variation around 1. In this slide, we can see the results from the rheological measurements I conducted on the hydrogels. I wanted first to see what was if there was any effect of the tannic acid on NFC that could be evident through the values of G prime and G double prime. In this case, I used the experimental values of G prime, G double prime in order to obtain fitted values, so they could be numerically compatible. Similarly, I also obtained exponents that are strongly associated to G prime, G double prime as they change as a function of frequency. So the ideal or an ideal gel should obtain almost identical M prime and N double prime. So the difference should equal 0. On the left side, we can see that the pure NFC or NFC as we have it in this experiment presents values of G prime around 4000 and values of G double prime around 500. And as we add various amounts of tannic acid, this case ranging from 1000 to 3350 milligrams of tannic acid per gram of NFC, then we can see that at the beginning there is a considerable drop in G prime, and then as we increase the content of tannic acid, there seems to be a greater stability of the system, and the final hydrogel, the one at 3350 milligrams of tannic acid per gram of NFC, has comparable values of G prime, G double prime to the reference sample containing 0 tannic acid. On the right side, we can see the values of the M prime, N double prime exponents. As you can see, as we increase the content of tannic acid, the gap between M prime and N double prime is getting smaller. This means that the gel is probably getting more stable, but this of course requires further experiments in order to validate these results. But as a first indicator, it seems that there is some relationship, some bonding between tannic acid and NFC. In this slide, we can see the results from the rheological measurement we conducted on silane. For this purpose, we prepare various concentrations of silane in aqueous solutions containing from 2.5 to 15% silane. The results show a large standard deviation and this indicates a great deal of randomness in the data. Also, we can see that the G prime is not increasing in proportion to the concentration of silane, which would be the most reasonable result, but that is not happening. Also, the M prime and N double prime as indicators of gel stability show a great deal of randomness, and this is not a result that goes or encompasses with the properties of gels. Differences were observed during hydrogels containing 1.5% total polysaccharide, 40% silane, 60% NFC, with and without tannic acid. In general, hydrogels with tannic acid exhibited smoother surfaces, more homogeneous porous structures, and thinner walls than those without tannic acid. Similar features were observed under optical microscopy, also at the University of Helsinki, but at greater magnification, silane and NFC were distinguishable components in hydrogel without tannic acid, as you can see in the micrographs A and C. What we can see on the foreground is what we consider to be silane, and the background is a smoother surfaced NFC. They both were clearly separated, and they're just mounted on one on the top of the other. Well, in the photograph B and C, it's very difficult to discriminate what is silane, what is NFC, which kind of indicates that they might have formed a stronger bond that was inexistent in the samples without tannic acid. In this slide, we can see the micrographs obtained from samples containing 3.5% total polysaccharide content, 70% silane, 30% NFC. We observed that these hydrogels were very similar in terms of structure, regardless of the presence of tannic acid. At greater magnification, though, silane and NFC were easily discriminated in hydrogels without tannic acid. As you can see on the right side, the micrographs B and C have a structure that seems to be made of beads. We're not sure what these beads are made of, but we believe that these beads might be just this might be complexes, silane tannic acid complexes. These beads were not found in the samples without tannic acid, I mean in photographs A and C, which follow the same pattern as before. We could see a structure that is very rough, mounted on the top of what seemed to be the NFC. Our conclusions are that there is considerable evidence that suggests that silane and tannic acid form complexes, thereby altering the type of interaction with NFC. The sharp differences in the morphology of hydrogels with and without tannic acid gave hints on the degree of interaction between silane and tannic acid complexes and NFC. Tannic acid alone might have an effect on hydrogel stability, but this requires further testing. Besides, silane, at least the type of silane that we used in this experiment, was not the kind of material that could form gels by itself. These are some of the references I used, and these are just some pictures from my time in Antibes. I am an amateur photographer, so I took the chance to take some snapshots of the location, and I truly enjoyed my time there. I learned a lot. I am relatively new when it comes to the rheology, but The guidance of Professor Buttaba was really good, and I really enjoyed and learned a lot there. Thank you so much for supporting my trip there.